want to calculate the pH of a buffer that results from the mixing of these two things. Now, you notice the key word here is mixing. So that means that it tells me how many milliliters I have of each one, but I need to find out what is the concentration within that mixture. So for each one, so here's my first one, and then this would be my second one. I need to actually calculate the moles and then divide by the total volume. So I'm going to try that first, the first one, and let you do the second one. So I'm going to have 0.250 moles per liter times 0.0600 liters, and that's going to give me 0.015 moles. And then make sure you label it so you don't lose track of which is which. So this is going to be the acid. So this is the moles. Now, what was the total volume in liters? So I'm going to have to take that number, and I'm going to divide by the total number of liters, which is 0.075. How did I get that? I added 60 plus 15. And when I do that, I'm going to get I'm going to get 0.200. So what I want you to do is I want you to try the other one and then come back and check your answer. So here is the second one written out. I started with my molarity, I multiplied by my volume in liters. I obtained this answer and divided by my total liters to get 0.100. So we need to find the pH, so that means that we need the hydronium concentration. And which one of these is going to give us a hydronium? Well, we know the salt is soluble, so that's not going to work, so it has to be the acid. So we're going to start with the acid. And we know that if it's a solution, it is in what? It's in water. We also know that it is at equilibrium. So it is going to make the hydronium ion plus the anion of the acid, which is the CHO2 minus. So what are my initial concentrations? That's what we found in this section up here. So make sure you use what we found and not what was given. So the initial concentration for the acid, that's the first one, is 0.200. Water doesn't count. We didn't have any hydronium. Here's your salt. So this is 0.100. And how does that change? Well, it's a minus x on the left. It's a plus x on the right. We've got two of those over here. And then to find equilibrium, remember we're going to add straight down. So I've got 0.200 minus x. I've got an x. And I've got 0.100 plus x. So as always, what we want to do is we want to see if we can do the approximation. Doesn't take any time at all, right? So let's do that first. If you don't know what the K sub A value is, make sure you look in the chart. However, it is 1.8 times 10 to the minus fourth. That's going to equal to the product. So I've got x times 0.100 plus x divided by 0.200 minus x. If I do an approximation, that becomes x times 0.100 over 0.200. And when I do that calculation, what I find for x is 3.6 times 10 to the minus fourth. I need to do what with that? Well, I need to divide that by the initial concentration, which is the 0.200. And then what do I need to do with that? Well, I need to multiply it by 100. And in doing so, is that number less than 5%? And I got 0.18%. So that is, we can use the approximation. Now what are we going to do with that? So since the approximation worked, we know that this number we obtained is the hydronium concentration, but we want the pH. So we're going to say that the pH equals the negative log of the hydronium concentration. And then I need to plug in what is that value. So I'm going to have equal to the negative log of 3.6 times 10 to the minus fourth. And let's see, when I do that on the calculator, I get 3.44. Remember, you want two significant figures after the decimal.